said earlier. I can have many amplification. I'm not going to just make a big amplifier and amplify everything, because this is not good from the noise perspective, which I will show you later through this Fritz equation. We'll start with different stages. Of course, more stages is more difficult to design, more area, more power consumption, and even run into oscillation, right? Easier. But anyway, we assume that we have a signal here. Then you have an output impedance, which will present me the noise of how much? What's the noise of output impedance of RS? 4 kTRS. Then I go through the first stage. Again, I extract the noise due to stage 1. Okay? Vn1 square bar is the effective noise generated by the amplifier presented at its output. And similarly, Vn2 square is the noise due to stage 2. Again, this is not the total noise you see eventually. It's not the noise due to the source plus stage 1 and then you give this. No. Here is just a model for this amplifier. You use this amplifier, you get an ideal amplification. At the same time, you add this noise to its output. You get ideal amplification, and then at the same time, you add this noise to its output, right? So I need to emphasize this whole thing is just the model of LN8. I still call it low noise amplifier 2. It's just a model of it, right? This is what I want to emphasize. Otherwise, you will go into the loop, like keep thinking, then should I keep adding the noise? Okay. The question is, what is the noise figure of this circuit? Of course, it's going to be a function of the noise figure of stage 1, noise figure of stage 2, noise figure of stage 3, etc. And our goal is to find out the equation so that I don't need to derive everything from scratch. So, okay? But before that, I also need to talk about one more thing that we discussed earlier. You see that I have an input impedance here. Out-in. Correct? This also has an output impedance. What it means, if you look at me, stage 2 look at stage 1. I see that you actually present me an output impedance, out1. Stage 1 look at the source, it sees RS, and itself present the impedance of out-in1 to the source. From stage 2 perspective, this whole thing is just a source from stage 2 perspective. Do you agree? It doesn't need to know exactly how you get anything. To me, you are just giving me something, right? Like your parents pass money to you. The money can come from your grandparents, great-grandparents. You don't need to know exactly how much they pass your parent and how much your parents spend. All you care is how much they pass to you. That is the R1, right? So we have talked about the alpha before, remember? The alpha at this point what is the alpha at this point? It means whatever you give me, it got discounted due to this potential divider effect. Let me call it alpha 1. It's out in 1 divided by RS plus R in 1, right? Make sense? Similarly, can you tell me at this point, it's getting messier, what is the alpha 2 at this point? Someone tell me? Do you agree with what he said? Do you agree? Basically, if R1 try to give 1 volt to the next stage, how much voltage does the second stage feel? He said it's 1 volt times R in 2 divided by R out 1 plus R in 2. Can you tell us why you say so?
Because it only sees the noise from
Right. We are not even talking about the noise, right? We're just talking about potential divider, right? So what does it say? C? Say again. You only see R1. Just like here, this guy only see RS. This we in give stage 1 something, but it has output impedance RS. And I have input impedance R in 1. The ratio is R in 1 divided by RS plus R in 1. For stage 2, it gets something from stage 1. Stage 1 gives you something, but it only sees R out 1, right? And its input impedance is R in 2. So that's why alpha 2 is R in 2 divided by R out 1 plus R in 2. Because I can model the whole thing. I don't care how complicated stage 1 is and what it takes as input. Stage 1 is nothing but just this. I can call it stage 1 output. It is just like this. R out 1, and then it goes to R in 2 of the stage. You see this? This is exactly the same as what I drawn here. RS, and you see C in, right? That's why your circuit get V in times R Z in divided by RS plus C in. Do you see this circuit? Whatever you give me, you have this output impedance, I have this input impedance, then I will only get Z in divided by the sum. Same here. Whatever you give me, stage 1 output, you have this output impedance, I have this input impedance, I only see R in 2 divided by the sum. Yeah, this concept is not trivial, but I hope you understand what I mean, right? So we have different alpha in these 2 stages. Okay? Any questions? And then we are going to have a lot of math after this. So no question, right? So I'm going to move forward. Okay, so first of all, I want to find the total gain of the circuit because we want to prove something later. What is the total gain of the circuit? Can someone tell me? But first, what is the definition of the total gain? Let me call it ACO. What is the definition of total gain? When someone tell you that the total gain of this whole thing is 5, what is the meaning of 5? What divided by what? Excellent. V out over V in. Can I express it as the gain of AV1 and AV2? Naively, you will think that is AV1 times AV2, right? Because I have 2 stages. However, do not forget we have this alpha 1 and alpha 2. You get discounted, right? So what you really have is, first you get discounted by this potential divider, R in 1 divided by R in 1 plus RS, and then you multiply this by AV1. And then you get discounted again by R in 2 divided by R in 2 plus R out 1, and then multiply that by AV2. This is alpha 1, this is alpha 2. Make sense? Because whatever you did, only this voltage goes to the amplifier. The amplifier only feel this voltage. You give 1 volt here, 1 volt here. Here you only get maybe 0.5 if they are the same. So you get 0.5 and then you amplify by AV1. Then again you get this counter again and then amplify by AV2 and then you get the output. So this is the total gain of this circuit. Is this okay? Yeah, so I hope that now you are very clear that someone give you a gain of AV1, it's just in ideal case. If you don't have the right impedance matching, you won't get the maximum gain. And here's the voltage gain, okay, voltage gain. Okay, then what is the equivalent output noise? V N out square. What I'm asking is, if I try to make this one just an ideal thing, and then eventually I want to put this V N out square, right? And this is combined. So I just put everything together. Now I don't have the noise source, the source noise, because it got amplified to here. Everything goes to there, right? What is the equivalent output gain, output noise? I claim that it is, I will just write it because that would be easier. It's Vn2 squared, okay, plus Vn1 squared. Let me just times R in 2 squared divided by R in 2 plus R out 1 square times AV2 square. Okay, I gave you the answer. Can someone explain to me what it means verbally? Very good, very good. So he's saying this. If I combine these two, so I am wrong, this does not include the source noise, okay? If you combine these two amplifiers, the total noise I see in the output, of course, first is the noise due to stage 2. This is at the output already. But besides that, I also have the noise coming from the stage 1. But it's not at the output yet. It's going to be amplified by the alpha 2 square and the AV 2 square. Because the voltage is amplified by this or reduced by this potential divider, and then times the gain, right? So that is the total noise due to the amplifier, right? So maybe I should make this so you can understand better later. This is the total noise at the output due to all amplifier. Okay, both amplifiers, right? We just transform it to the output. That's it. Right? Why do we want to do this? Because again, we want to use this equation. Because this equation, Vn squared, is about the total noise at the output due to the amplifier that we derived earlier. Okay? So because of this, then I know that the noise factor of the whole circuit, the total noise figure, is going to be equals to, I just use the equation 1 plus Vn square out divided by A0 square divided by 1 over times 1 over 4 kTRS, right? Very messy, but we can make it out. We already derived this equation for one amplifier. But this one amplifier can be a combination of many amplifiers, right? So what we are saying is just that anyway, if we treat both as one amplifier, the total output noise, Vn out squared, divided by the total gain, including this resistor divider, potential divider, and then divided by the 4 kTRS, would be the plus 1 will be the noise figure. Are you able to map this? Any questions? This 4 kTRS is VRS square here. 1 is 1 here. Vn square out square is this one. A0 is this A0, right? Is this whole thing. Yes, I put A0. So A0 is already have alpha here. So let me write it out. That might be that would be easier for you to see. So now we have a very long equation. Let's look at this. This is going to 1 plus, and then I'm going to substitute this whole thing to here. This whole thing into here. This whole thing into here, okay? So I will first, it's complicated. Let me just put everything. Vn2 square plus Vn1 square. So I'm going to substitute this with alpha 2 square. AV2 square. Is this okay? Because this is alpha 2 square. Let me just remark this is alpha 2 square. So okay, I substitute this whole thing. And this whole thing is divided by A0. Again, A0 is alpha 1 square. A0 square, AV1 square, alpha 2 square, AV2 square, and then 4 kTRS. Okay? Again, this one is this one, right? And here I just substitute A0 square, which is alpha 1 square, AV1 square, alpha 2 square, AV2 square, and then 4 kTRS. Make sense? Yeah. Where? Say again, I cannot hear. Total noise here. Because, so that's a good question, because AV2 is right at the output, right? So I just copy AV2. And VN2 is at the output, right? So I just copy VN2. But VN1 is here. So it has nothing to do with AV1, right? It got amplified directly by the next stage, right? So then that's why you only have AV2. Amplified by next stage 2 appear here. Make sense? Oh, okay, good. So now then let's continue, right? So I will be able to write this as 1 plus, I will start with the second term, so maybe it is easier if I swap this. I just put this to the end, plus Vn2 square. I just move it to the end. I just swap it, okay? So the first term, you see many things got cancelled. Alpha 2 square, AV2 square got cancelled. Then you only have this. You have Vn1 square divided by alpha 1 square, AV1 square. Correct? And the second term would be, I of course still have this 4 kTRS, 1 over 4 kTRS. Then the second term is Vn2 square divided by a very large term, right? The whole gain, A alpha 1 square, AV1 square, alpha 2 square, AV2 square over 1 over kTRS. So our goal is to find out how the total noise figure related to the noise figure of each term. First, look at this. can you recognize what this is? 1 plus Vn1 squared divided by the gain alpha 1 AV1 squared and normalized to the source impedance. What is this? The noise figure of the first stage. Yes. This is just the NF1. How about this one? You don't know. You cannot see it now. It's complicated. Okay? But no problem. We will continue on the second stage, right? The third term. This one, see next page. So we continue to work on this term, right? So let's see what happened. So because we want to represent this as a noise figure of the second term. So naturally, of the noise figure of the second stage. Naturally, let me write it down, what it has to be. Again, it is 1 plus what? The Vn2 squared divided by AV2 squared times alpha 2 squared, right? Divided by 4kT R watt. Huh? Very good, very good. Instead of Rs, is R out 1. Excellent. Let me check my cheat sheet. Okay. Now my goal is to transform this term so that it becomes this term. Okay. So let me transform it. So I just put 1 to the left, noise figure of 2 minus 1. I want to have Rs there, so I'm going to multiply the whole thing by R out 1 divided by Rs. Then the right will be Vn2 squared divided by AV2 squared alpha 2 squared 4kTRs. Right? Because Rs can get cancelled, R1 come down, then I get back to the original one. Now, it's difficult to see, but let's compare this one. This is what? Vn2 squared divided by the alpha 2 squared, AV2 squared. I missed the 2. Right? And divided by 4kTRs. AV2n squared divided AV2 squared, alpha 2 squared divided by 4kTRs. The only difference is that I have an extra alpha 1 squared, AV1 squared, right? So it means that the last term, so the last term from the previous page equals to the whole thing, NF noise figure of 2 minus noise figure 2 divided by, I'm going to put Rs divided by R out 1 here, and then the whole thing further divided by AV1 squared, alpha 1 squared. Yeah. So our conclusion is that the total noise figure equals to the noise figure of the first stage. Or better yet, I want to write it as 1 plus the noise figure of the first stage minus 1, right? Anyway, 1 is going to get cancelled, right? I write it in this way because I want to have noise figure 1 minus 1 of the first stage 1 minus 1. Plus the noise figure of the second stage minus 1 divided by this special term, AV1 squared alpha 1 squared Rs divided by R out 1. So you already see something interesting. If you cascade 2 stages, the final noise figure really determined by the first stage noise figure. the second stage noise figure is going to be reduced significantly by the gain of the first stage. Your gain of the first stage is 10, this is reduced by 10. But it's not exactly the gain. It normalized by something called Rs divided by R out. And we have a name for this. This is called the called the available power gain of LNA1. This is the something called available power gain of the previous stage. I will prove it. But the message is that the noise figure of the next stage got discounted by the available power gain of the previous stage. That's why the noise figure is not that important in the subsequent stage. So just now you asked, how do we design it? In the first stage, make one with very low noise figure. Maybe the gain is not great, but I want it to be low noise figure. And then the second stage, you increase the gain. Even you have a worse noise figure, it's divided by the available power gain of the first stage, right? So here I want to talk about what is the available power gain.